Mathematicians often call this the most beautiful equation ever written, not because it's complicated, but because of what has to come together for it to exist. This equation is usually shown as a single line, but really it's a meeting of ideas, each coming from somewhere very different. The question is, why do they end up in the same equation? Throughout history, mathematics wasn't always a unified subject. It was built as separate areas, each focused on a different type of problem. By the early modern period, several areas were already well developed. Algebra, geometry, the mathematics of change, and even imaginary numbers had started to flourish. These areas used different tools, they asked different questions, and for a long time, rarely overlapped. By the 18th century, that began to change. Mathematicians were no longer studying isolated problems, they were studying what creates them. Euler, one of the greatest mathematicians of all time, was one of the first mathematicians fluent across all of them. I mean, just look at his contributions. He worked at the point where these areas overlapped. He didn't set out to unify mathematics. He was simply trying to understand how functions behaved. One function in particular kept appearing in his work, the exponential. It showed up in problems about change and in problems about motion. At first, that isn't surprising. It's often said that Euler invented it. He didn't. It was already very well known in mathematics. What he did do is he recognised how fundamental it is, so much so that it's now directly tied to his name. He followed it further than anyone before him. What caught his attention was its consistency. The same function returning in completely different problems in different areas. This wasn't a coincidence, it was a pattern. It moved freely between the branches of mathematics, and Euler recognised that this matters. Once a function behaves that reliably, you begin to ask how far it extends. Euler followed that question to its edge, and that's where this equation begins. Let's focus on the more general result, e to the ix equals cos of x plus I sine of x. The more familiar identity that we know comes from a later, simple substitution. Euler started with how the exponential function is defined. You see, we can write e to the x as an infinite sum through the Taylor series. It's a way of building the function out of simpler polynomial terms. He then made a simple but unusual decision. He replaced the real input with an imaginary one, I of x. Following this, he simplified the powers and was left with a series of real and imaginary functions. By splitting these and focusing on the two parts, Euler recognised something quite cool. It's about recognising patterns, you see. The series made up of real terms matches that of the cosines Taylor series, and the imaginary terms, once you factor out I, matches the Taylor series for sine. Knowing this, we can rewrite this back into the general form. And finally, just sub in pi. Voila. So algebraically, that's where this equation comes from. But if we stop there, it feels a bit abstract. We've shown how it works, not why it works. And that's because the algebra is doing a lot of the heavy lifting. It tells us the result, but it doesn't tell us what this equation is actually describing. To see that, let's step back and appreciate the geometry. Consider the complex plane. Draw a circle that is exactly 1 unit from the origins at all points. Take a point on that circle. Given only the angle changes, we'll call this angle x. With this knowledge, we can call the vertical component sine of x and the horizontal component cos of x. So at any angle, the point has coordinates, cos of x, sine of x. The point is completely determined by the angle. Change the angle, you change the point. Varying the angle traces out a rotation. This rotation has a compact description, written as e to the ix. So from wait, but why? I had to stop and rethink if I actually understood why this causes rotation, and honestly, I couldn't say I did. So while doing some further research, I discovered this explanation that really facilitated the concept for me. The key shift for me was to stop thinking about this as an exponential, and more like a repeated multiplication. If you've seen a parametric circle before, this should feel familiar. Adding a fixed amount repeatedly wraps you around a circle. Multiplying by I does a very similar thing. Each multiplication changes direction rather than size is just a continuous variation of that idea. Instead of stepping around the circle in jumps, the angle changes smoothly. That's why the point is only rotated and not extended. Thank you, SL, for your 2013 repost. That's helped me immensely. Alright, back to this. Here is really a story about changing angles. Change the angle, you change the point. Substitute pi into the function. Geometrically, this rotates the point to where the angle is pi, relative to the positive real axis. The point is now placed at -1. Simplify the expression, and bam! Up to now, everything we've looked at has stayed inside of mathematics. We've talked about angles, rotations, and even series. That structure doesn't disappear once you leave the page. It's everywhere around us. Take something like a wave. At first, this just looks like a curve moving up and down. But mathematically, that motion can be described as a rotation. Each oscillation corresponds to a point rotating at a constant rate. Now here's the key idea. Real signals are very rarely this simple. In fact, they're usually very complicated. But any complicated signal can be built by adding together many simple rotations. To actually work with those rotations, we need a way to move between rotation and oscillations. That's exactly what Euler's identity allows us to do. It tells us that a rotating exponential is related directly to sine and cosine waves. That translation is what makes Fourier analysis possible. But that's a story for another video. So when mathematicians call this the most beautiful equation, they're not talking about how it looks. They're talking about what it connects. Numbers that came from completely different problems, from different areas of mathematics developed centuries apart, all meeting in a single equation. That's the beauty of it.